work done by forces. Next question is, can we compute the work done by moments or the torque also? So let's look at that. So work done by torque. Okay, so let's say I have a beam, and this beam is constrained to rotate about 0.0. Okay, so we have hinged it over here, and I can connect a motor over here right at this point, and that motor is going to, let's say, rotate this beam with some torque. Okay, let's say that torque is given to as st. So the question is, what is the work done by this torque? Clearly that there will be some work done by the torque. So the question is, what is that work done? So we already know how to compute the work done by force. We can replace this torque with what we call a force couple. So this can be replaced via, we'll draw this beam again, and this is where it is constrained to rotate. I will replace this torque with a force couple. So force couple is basically one force at a certain distance away. We'll call this, let's say, distance r away. We can pick whatever this distance is, and then on the opposite end we will again pick our distance r and have the same force F point in the opposite direction. So now the effect of these two forces pointing in the opposite direction a little bit away from point O is that if you take the moment about point O, if you compute the moment about point O, what do you get? You get F times r, that's in the counterclockwise direction, and then due to this F we will get another F times r, and that would be equal to 2F times r, right? So if you are given a torque, which in this case is now this equal to T, right? That's what you were given. So the torque about point O is equal to this 2Fr, which means F is equal to T over 2R. So if you pick your R, then you can find what your F would be, right? So if your R is larger, then F would be smaller. If R is smaller, then your F would be larger as a result of it, right? But the basic idea is that you have replaced this one single torque or the moment applied by a motor with a single force couple. Now the advantage of doing a force couple is that if you look at the net force on their beam, it is actually 0, because this is pointing towards left, this is pointing towards right, and if you add them together they will cancel out. So as a result, there is no net force on it, which is what you want, because if there was a net force on this beam, then you wouldn't really have a pure moment situation, which is what you have in your original problem, where there's only one torque, there is no net force on it, right? So you could not simply get rid of this and say, okay, I've got a force couple, okay, because then you would have a net force F in this direction. All right, so let me redo this. I'm going to draw this again, and that's my force F at a distance r, and this is my force F at distance r from here. Okay, all right, so now we have replaced the torque, a pure moment or a torque, with a force couple. We can talk about what is the work done by each of these, right? We already know that definition. So the work done is integral dw, which is integral F dot dr. Okay, so in this case it would be, so dr is basically ds, so that would be basically F ds. Both of them are along the same direction, right? Because this is the direction of the ds, this point P, this is point Q. Point P is moving in a circular path with O as the center. Same thing is happening with the point Q. So both F and ds are pointing in the same direction, and that would be 2F ds, because you have this force and they have this force, right? So that's 2F ds, and that's your work done. Okay, now what is F itself? F we have seen is equal to 2 times T over 2R ds, right? So this cancels, so we get T times ds over r. Okay, so first of all, this is all integral here, which I missed. Okay, now what is ds? Well, ds is equal to r times d theta, right? We know that, so we can substitute that. So T over r, r d theta, so r cancels, so we get integral T d theta. So if T is constant, I can take it outside, but in general it does not have to be. So the work done is equal to integral T d theta. If T is constant, let's say T0, then work done is equal to T0 times integral d theta would be total delta theta. So that's the work done if the torque is constant, which would happen quite often. So if you are, let's say, given a gear, let me do an example. You have a gear or a wheel or a disc or a pulley, and there's a motor connected over here, and I tell you that the motor is applying a torque of 5 Newton meter on this thing, then in, let's say, 10 revolutions. So in 10 revolutions, what is the work done? What is the work done by the motor? Okay, so that's the question. So the motor is applying a constant torque of 5 Newton meter, and then in 10 revolutions, what is the total work done? Okay, so we can find that work done is equal to T times delta theta. The torque is given to you as 5 Newton meter. Delta theta has to be in radians. Remember, all these have to be in radians. So 10 revolutions is how many radians? One revolution is 2 pi. So 10 revolutions will be 20 pi, right? So that will be 20 pi. So that will be 100 times 3.14, which would be close to 314 joules. That's the work done by a motor to rotate a gear by 10 revolutions when you know what the torque amount is. So that's how we compute the work done by a torque.